we've talked about momentum, right? We've talked about impulse and how they're related and all of that fun stuff. This mask is just so loose today. It's annoying. Okay, so now we're going to talk about conservation of momentum. And what conservation of momentum basically means is that it's requiring, what do you think it requires to be zero?
It requires, what did you learn? The momentum and the impulse.
It requires a total force to be zero. Okay? Now, if you're thinking about, well, force isn't in momentum though. But it is, right? Because we learned that impulse is equal to force times the change in time, which is equal to final momentum minus initial momentum, okay? And whenever the total force is zero, doesn't that mean this change in momentum has to be zero? And if the change in momentum is zero, doesn't that mean momentum was conserved? Okay? So think about it. That means that whatever initial momentum you start with is the exact same momentum you end with if we have conservation of momentum. Okay? So total force to be zero, and our initial momentum will equal our final momentum, okay? And now get ready for probably one of the worst drawings I've done all year. I know, right? This is a bike, and you're riding it, and you're just gonna say, okay, Miss Bernal. No, this is a bike. Okay, just leave me alone, you guys. And you're riding the bike on a road. Okay? Now, there are two kinds of forces that we want to think about when we talk about conservation of momentum, okay? They're called internal forces and external forces. So how these work? We think about things as a system, okay? So right now with you on this bike, you and the bike, just you and the bike, the road is not included. You and the bike are a system. Okay? You're a system. And whenever you act on the bike or the bike acts on you, it's called an internal force. So an example of this internal force would be, have you ever pushed hard on the handlebars of your bike? Or pulled on them or anything like that? I mean, you hold them, so you have to pull them or push on them at some point, right? Mm-hmm. Does just touching the handlebars change your speed? No. So does it change your momentum? No, okay? So internal forces do not cause the momentum to change. They do not cause a change in momentum, okay? Internal forces do not cause a change in momentum. Now, I said there's also another kind of force, didn't I? External forces, okay? External forces would be like your wheels acting on the road, okay? So think about this. When you're pedaling harder, that gets into your wheels, right? And then your wheels move faster. Does that increase your speed? Yes. So the wheels on the road is increasing your speed, right? So is that a change in momentum? Yes. Okay. So external forces, an external force causes a change in momentum. So it will cause a change in momentum, okay? An external force will cause a change in momentum. Because if speed changes, does the momentum change? Yeah. When speed changes, momentum changes. So, how we're going to represent this, since you know how we talked about a total force, okay? What we're going to say is that our total force is equal to summing up all of the internal forces plus all of the external forces. Okay? But what did we just say all of the internal forces are equal to? So our total force is only going to be equal to what? Our external forces, okay? And don't worry, we're going to draw another example to try and get how this is true and how this works, okay? I'm only going to erase my one ugly picture so that I can draw another one, don't worry. I should call it a what? No, because sometimes when you pull on a horse's reins, it still ends up causing the horse to stop. Okay, so we've got 2 canoes. Okay, and in each canoe, there's a person. So, like, this person's waving at you. They're saying, "Hi, how's it going?" This person is like, "Get away from me." Okay? We'll call this canoe, canoe 1, and this canoe, canoe 2. Canoe, canoe. Okay. So, when this person in canoe 1 pushes on canoe 2, they're exerting some force on canoe 2. Is there any force getting exerted on canoe 1?
No.
Oh, okay, let's think about, wait, but we need to know why, okay? Didn't we learn about Newton's laws? What was the first law?
An object in motion stays in motion once acted.
Yeah, good. An object in motion stays in motion, object at rest stays at rest, and that's acted on by an outside force, right? What was Newton's second law?
Something about an accident.
No, it's F equals ma. The first law is the law of inertia. The third law is that every action has an equal and opposite reaction. So when we push on canoe 2, canoe 2 pushes back on us with the exact same force, equal and opposite. It's called an equal and opposite reaction pair, okay? So however you push on something, it pushes back the same way on you. So that's why when you're riding your bike and you're pushing on the handlebars, you're not moving it forward because the handlebars are doing what? They're pushing back on you, okay? So this is why internal forces do nothing. They cancel each other out. They cancel each other out, okay? So, internal forces occur in what kind of pairs? Equal and opposite, right? They occur in what kind of pairs?
Equal and opposite.
What kind?
Equal and opposite.
That would be a really good quiz question, wouldn't it be? I feel like it would be. Okay, now, because these internal forces occur equal and opposite, what does it cost to always be 0? The total summation of the internal forces, right? Will always be 0 because these occur in what kind of pairs? Okay, so that means that our total force will be equal to what? The sum of the external forces. The good news about this is if you're ever doing a question like in your problem set tomorrow maybe, and it mentions internal forces at all, do you have to do anything with them? No, we get to ignore internal forces. If only we could ignore our internal thoughts and feelings.
That was very deep.
Right? Should have been a lit teacher. Yeah. No, I shouldn't have been. I still can't really spell very well. So, now let's talk a little bit more about the actual idea of conserved momentum, okay? So when we talked about conservation of energy, right? We had that the initial potential plus the initial kinetic was equal to the final potential plus the final kinetic, right? So we have something very, very similar with potential, okay? How we think about potential is that, let's say, the initial potential of potential 1 plus the initial potential of potential 2 plus the initial potential of potential 3, and so on and so forth to some arbitrary number. Remember, you guys, that's what that stands for. That's initial. So that could be all the way up to 20. You never know, okay? It's all equal to the final of all of these sums. Now, there's something that I want you guys to notice about this. Over here, it would just seem like it was one particle, right? When we actually do conservation of momentum, does it look like it's only one particle? No, okay? This is the total momentum of a system. Total momentum of a system. It is not the momentum of each individual object. And what's important to note here is that the momentums can vary, okay? What I mean by that, you guys know how we just said that sometimes we would be like, okay, the potential here starts with 5 and 11, okay? We had 5 potential, 11 kinetic. Well, maybe that means that's 16, so maybe we end with 8 and 8 at the end, right? Isn't it still conserved? So the same thing can happen with these, all right? I could start with 3, 4, and 5 and end up with 6, 3. What would my other one be? If I have 3, 4, and 5, and then 6 and 3, what would the other one be? 3. That can happen because it equals, see you guys, 9, 10, 11, 12, 6, 7, 8, 9, 10. Oh, yeah, 6, 7, 8, 9, 10, 11, 12. It's 12 on both sides. Why did I put it over that one? That's where you guys are like, what? Sorry, that. Lord have mercy, you guys. I'm so sorry. It can be like that. I'm sorry that I did that to you. Okay? Went right over my head. I was just like, it's a P. Okay? So that's what it means by it can vary. All right? So you don't have to end with exactly what you started with, by meaning that the P1 still is going to have to be 3 on both sides. You just have to have the same overall momentum on each side, okay?